Yeah. Hello all. Welcome back to the session on transportation engineering. So in our previous session, we were discussing about uh, the desirable properties of materials until the aggregates we are done with. So one more material, next material we use for road construction. It is cement. So cement is used as a binder in the construction of cement concrete and cement grouted roads. So it is important to check the quality of cement before it is using as a binder. So some of the field tests for assessing the quality of cement are color, it should be greenish gray color, and some physical properties. So physical properties like if you thrust your hand inside the bag of cement, you should feel cool. And if you take a pinch of cement and feel in between two fingers, so you should get a smooth feeling when you rub it, and then there should not be any presence of lumps in the cement. It shows that if any lumps are there means it is the sign of hydration of cement in that, and it should be stiff enough. If you make a pat of cement and keep it inside water and take it out after that, it should be able to retain its shape. And there are some of the laboratory tests to assess the quality of cement. Various tests on cement is carried out for the assessing following purposes: to find the physical and chemical properties of cement, and to regulate various stages in the manufacturing process, and to understand behavior of cement after its use on the works. So some of the standard tests when it comes to chemical composition of cement, the presence of lime and alumina, it should not be less than uh, 0.66% and not more than 1.02%. And as calculated from by using this formula, which is shown. And magnesia, it should not exceed 5%. And under loss of ignition, it should not exceed 4%. Total sulfur content should not be more than 2.75%, and insoluble residue should not be exceeding 1.5%. These are all the requirement of chemical composition. And then when it comes to physical properties, first we check fineness of cement. First we have to, there are two methods by doing a sieving, and another method by using a permeability test method by using planes air permeability test apparatus. So in sieve analysis, what we'll do, we'll take a 90 micron sieve, and approximately 100 grams of cement is taken and sieved through 90 micron sieve for a duration of 15 minutes continuously. And after a minute 15 minutes, whatever the residue left on top of sieve, that should be weighed. So the percentage of residue should not be greater than 10% by weight for the taken cement sample. So it's a simple method to check the fineness of cement. If it is greater than 10%, that is not an acceptable type of cement for construction. And then fineness can be checked by using plain air permeability test also. So in this method, we are going to draw a definite quantity of air through the prepared cement bed of definite porosity 0.5. So to draw a definite quantity of air through the prepared cement bed of porosity 0.5, how much time it is taking, okay, that we are going to count over here. So higher the time it takes for drawing definite quantity of air means greater the fineness of cement. If lesser is the time, lesser is the fineness. So we have equation K into root T, where K is the apparatus constant and T is the time taken to draw a definite quantity of air through the prepared cement bed, 0.5. The apparatus we use over here, that is a plain air permeability test apparatus. It will be consisting of one YouTube manometer, and a standard liquid will be filled inside that, and there will be a pressure bulb to control the liquid at different levels. And next desirable property, it is a compressive strength of cement. So it is one of the important property the cement should possess. This one, how we assess the compressive strength of cement is cement alone cannot be made the specimen by mixing with water because of shrinkage issues. So as per these standards, you will have to get the mixture of cement and sand in a proportion 1:3. And for this, water you need to calculate. It is given by P equal to P, that is consistency, whatever it is required, P by 4 plus 3.5% by combined weight of cement and sand, where PA here it is a standard consistency water requirement. So that much amount of water you need to calculate and take. So mix it properly until you get the uniform mix. And standard cube size according to IS codal provision, it is 7.06 by 7.06 by 7.06 centimeter. This cube size will take. Make sure it is clean and the lubricant is applied inside, and start to fill the cement mortar in a standard manner, or you can place it on vibrating platform and you can fill it, compact it properly and finish it. After 24 hours you demold it, keep it for curing, and you can test it for a specified duration of 7 days of curing, 14 days of curing, 21 days of curing, and 28 days of curing. So after 28 days it is going to get its uh, highest strength. So compressive testing machine you'll use. So the loaded failure will be taken, and loaded failure divided by cross sectional area, that is 7.06 by 7.06 by 6. That is the area. If you divide, you are going to get the compressive strength of cement. So different grades of cement possess different compressive strength. So OPC 33, 43, 53. So this 33, 43, 53 represents the compressive strength of cement. If you have used OPC 53, at least you should get 53 Newton per mm square compressive strength. Next, it is a consistency of cement. It is important to assess the standard consistency or normal consistency of cement. This is the water content which is going to be used for conducting other laboratory tests like initial setting time, final setting time, soundness test, compressive strength, all this. So in this, what we'll do, we'll be having wicket apparatus with a Y-cut mold, and there will be different needles and plungers. In case of consistency, we'll use plunger. In case of setting time, we'll use needles, different needles for initial setting and final setting time. So approximately 300 grams of cement will be taken, and you can start with around 20 to 23 percentage of water. So make calculate around approximately 23% of by weight of cement. That much amount of water you calculate and gauge it properly, and fill this prepared cement paste inside a Y-cut mold. Y-cut mold should be placed on a non-porous glass plate to make sure that water is not going to be lost, and flat surface you are going to get. So fill the cement paste inside it. So place this mold below the plunger which is placed in Y-cut apparatus. Bring the plunger until it touches top surface of cement paste and allow it to penetrate inside. And the depth of penetration you observe. So depth of penetration, if it is coming in the range of 5 to 7 mm, means that is that particular percentage of water will give a consistent cement paste. So that can be expressed as normal consistency value or standard consistency value. So if it is not penetrated, if it is less than 5 mm, so in such case go for increasing the water content. So from 23 to 25 you can go for, or 26, 27, like that. Keep increasing water content until you get the depth of penetration of the plunger in the range of 5 to 7 mm. So that particular percentage of water you express it as normal consistency or standard consistency. So after getting the value of normal or standard consistency, you can go for determining initial and final setting time. So these are all important properties of cement, initial and final setting time, which will control on the duration of mixing, transportation, placing, finishing of cement, concrete, and all. So initial setting time, it is the time elapsed between the duration or time at which water is added to the cement to the moment at which the cement starts to lose its plasticity. So this elapsed time is known as initial setting time. So that this time says that by within this specified time, the cement products, that is cement concrete, should be mixed, transported, and placed and finished. Okay. So here also 300 grams of cement we are going to take, and we have to take water 0.85 times of normal consistency value. That much amount of water we take, we mix it properly, gauge it properly, and then fill it in Y-cut mold in a standard manner and place this Y-cut mold below the wicket apparatus. So it will be consisting of a special needle for IST, that is 1 mm by 1 mm cross section square needle you will be having. You bring this needle until it touches top surface of cement paste and allow it to penetrate. Observe the depth of penetration, and before that the moment at which water is added to the cement, that time should be noted down, and allow it to penetrate this needle. Depth of penetration you observe, you may be getting some 0, 1, 2, 3 mm, whatever it may be. So you observe at which particular instant of time the depth of penetration of the needle is 5 to 7 mm. So for every interval like 5 or 10 minutes, you keep observing until you get 5 to 7 mm depth of penetration, and finally you get the value of initial setting time. So when the moment at which water is added to the cement and the moment at which the needle have a penetration in the range of 5 to 7 mm. So that time is called as initial setting time. And then final setting time, this is the time elapsed between the moment at which water is added to the cement to the moment at which cement completely lost its plasticity. That is called as final setting time. So in place of initial setting time needle, final setting time needle should be placed. So same cement paste which is used for initial setting time, same thing can be used, same specimen can be used to bring this final setting time needle until it touches top surface of cement paste and allow it to penetrate. See here, you need to observe the impression made by the final setting time needle. So it will be consisting of one cross head with a projection of needle. So you'll have to wait for a duration when the needle makes its impression, but the crosshead which is attached to the final setting time needle fails to make its impression. So that time you need to note down. And finally, you express final setting time as the time elapsed between the moment at which water is added to the cement to the moment at which the crosshead attached to the final setting time needle fails to make its impression. So that's all about a final setting time. Next, it is a soundness test. So we expect the cement to be sound enough when we use. And the IS codal specifications for initial and final setting time, it should not be less than 30 minutes for initial setting time. It should not be greater than 600 minutes in case of final setting time. And soundness, we expect cement to be sound enough, and it should not change its volume once it is used. If the cement is going to be changing its volume once it is used for the construction of any structure, that is going to generate some extra stresses once the concrete get hardened, due to which cracks may come in concrete structures. So it is good to check the soundness of cement and make sure that you are going to use a good quality cement which is sound enough. So it will be consisting of one Lee-Chatelier apparatus to check the soundness of cement. So dimension of this Lee-Chatelier apparatus are 30 mm diameter and 30 mm height as shown in figure over here. And it will be consisting of two indicators, and there will be a slit in this cylindrical portion, and that width should not exceed 0.5 mm in sharing. So prepare cement paste. Take certain 100 grams of cement, certain quantity, and then calculate 0.78 times the normal consistency value of water. That much amount of water you calculate and mix it properly and make the cement paste. Fill that prepared cement paste inside this Lee-Chatelier apparatus. Place non-porous flat glass plate at the both open ends of Lee-Chatelier apparatus, and firmly you fix it and measure the distance between two indicators initially. and then place it in water bath. So about 30 minutes you will have to place it in water, and then boiling you need to start. You need to boil the water, and the mold is removed from the water, and it is allowed to cool. So they should be done for a duration of 24 hours and maintain to a temperature 24 degrees Celsius initially. So that is for getting a meters, and this distance should not be greater than 10 mm. If it is greater than 10 mm, means it is that after hydration, the product of hydration of cement are increasing in volume, so that an internal stresses it is going to generate. So that's all. A few experiments on cement, which is used for cement concrete road construction. Next, it is design of highway pavements. So some of the objects and the requirement of pavements, it is the objective of a well-designed and constructed pavement is to keep elastic deformation of the pavement within the permissible limit, so that pavement can sustain a large number of repeated loads and its application during the design life. And there are different types of pavements are there: rigid pavements, flexible pavement, and semi-rigid pavement. So rigid pavement, these possess a worthy flexural strength or flexural rigidity. So its design is completely based on providing a structural cement concrete slab of sufficient strength to resist the destructive action of traffic coming on it. So because of its rigidity and the high modulus of elasticity, it tends to distribute the load over a relatively wider area on soil. The minor variations in subgrade strength have little influence on a structural capacity of rigid pavements. In the design of a flexural strength of concrete is the major factor and not the subgrade strength. So it is important to make sure that a better flexural strength concrete you are going to use. So it is because of the fact that when subgrade deflects beneath the rigid pavement, concrete slab is able to bridge over localized failures and was an interruption due to internet connectivity. Okay. So there are different types of payment structures are there: rigid payment, flexible payment, and rigid payment, semi-rigid payments. So it depends on its
Their screen off.
screen is not visible.
ಇಲ್ಲ ಸರ್.
Some internet connectivity issue I am facing in between. Yeah. So some of the difference between flexible and rigid payments. So flexible payment, it consists of a series of layers with the highest quality of materials at near the surface. Whereas a rigid pavement, it consists of one layer of a Portland cement concrete slab of relatively higher flexural strength. Flexible pavement will reflect the deformations of subgrade and subsequent layers on the surface of pavements. Whereas rigid pavement, it is able to bridge or localize failures and areas of inadequate support. Flexible pavement, the stability depends on aggregate interlocking effect and particle friction and cohesion, where the structural strength of rigid pavement is provided by pavement slab itself by its beam action. Pavement design of flexible pavement is greatly influenced by strength of a subgrade, whereas rigid pavement it is influenced by flexural strength of concrete is the major influence factor. Flexible pavement it functions by a way of load distribution through the different component of layers, whereas rigid pavement it distributes the load over wide area of subgrade because of its rigidity and high modulus of elasticity. Temperature variations due to change in atmospheric condition do not produce stresses in case of flexible pavement, whereas temperature changes will induce heavy stresses in case of rigid pavements. Flexible pavement have self-healing properties. Deformations occurring due to heavier wheel loads are recoverable to some extent. Whereas rigid pavement, excessive deformation occurring due to heavier wheel loads are not recoverable, that is, settlement is permanent in case of rigid pavement. So now you come for design of rigid pavement. Cement concrete pavements represent the group of rigid pavements. Here the load carrying capacity is mainly due to rigidity and high modulus of elasticity of the slab itself. So here the slab action is expected, and Westergaard considered that rigid pavement slab as a thin elastic plate resting on soil substrate, which is assumed as a dense liquid. Here it is assumed that the upward reaction is proportional to the deflection, that is P equal to K delta, where K is a constant defined as modulus of subgrade reaction, and unit of this K is kg per centimeter cube, that is kg per centimeter square per centimeter of deflection, that is nothing but kg per centimeter cube. Westergaard modulus of subgrade reaction, modulus of a subgrade reaction K is proportional to the displacement. So displacement level taken as 0.125 centimeter in the calculation of K. If P is the pressure sustained in kg per centimeter square means by the rigid plate of diameter 75 centimeter at a deflection of 0.125 centimeter, then the modulus of subgrade reaction K will be equal to P divided by 0.125 kg per centimeter square. And the relative stiffness of a slab to subgrade. So Westergaard defined the radius of a relative stiffness as EH cube divided by 12 times of K into 1 minus P square, where L is radius of relative stiffness in centimeters and E is the modulus of elasticity of cement concrete expressed in kg per centimeter square. Mu is the Poisson's ratio of concrete, that is 0.15 standard value, and H equal to slab thickness measured in centimeter. K is the subgrade modulus or modulus of subgrade reaction kg per centimeter cube. And some of the traffic parameters to be considered in the design of rigid pavements are design wheel load and traffic intensity. So design wheel load, when it comes to, it should be maximum wheel load of the predominant heavy vehicle likely to use the pavement in the normal course of pavement. It is currently taken as a 5,100 kg. The maximum tire inflation pressure for the vehicle should be ascertained to determine tire contact area through which the load is transmitted to the pavement. For most commercial highway vehicles, it ranges from 5.3 to 7.3 kg per centimeter square. And next parameter, it is a traffic intensity. So the passage of a traffic results in a repetitive loading of the pavement, thereby inducing fatigue effects in the concrete. So these effects, while not of the much consequence in case of low traffic intensities, because of the considerable time, there will be lag between the vehicles moving on it, the successive passes. Assuming greater importance in case of heavily trafficked pavements, as fatigue strength of concrete reduces with increase in number of load repetitions, it is required to sustain. For traffic prediction on main highways, the following correlation may be used, that is T equal to P into 1 plus R raised to N plus 20, where T is the design traffic intensity in terms of number of commercial vehicles, where its weight component should be greater than 3 tons, that will be considered, that is per day we are going to take. And P is the traffic intensity at last traffic count, R is the annual rate of increase of traffic intensity, and N is the number of years since last traffic count up to date of commissioning new concrete. So traffic intensity P for assessment of design traffic intensity T should normally be a duration of 7 days average based on 24 hours counts based on the growth rate of traffic over the past few years. A value of 7.5% is suggested for R for rural roads for the time being, whereas actual data are not available. Traffic classification is based on a design traffic intensity suggested for adoption of a rigid pavement design. So there are different traffic classification from A to G. If the design traffic intensity per day at the end of design life is ranging between 0 to 15, so it is classified as traffic A classification. If it is more than 4,500 and all the expressways considered under classification G, and it varies 15 to 45, 45 to 150, 150 to 450, 450 to 1500, 1500 to 4500 for the classified traffic condition B, C, D, E, F respectively. And some of the environmental factors also to be considered in the design of rigid pavement. First one, it is the temperature difference. Temperature difference between the top and bottom of the concrete pavements is a function of solar radiation which is received by the pavement surface at the location. Losses due to wind velocity, etc., and thermal diffusivity of concrete and is thus affected by geographical features of the pavement location. So as far as possible, values of actual anticipated temperature differences at the location of pavement should be adopted for the pavement design. I'll show you the equation how we'll use in, uh, in the next few slides. And then the mean temperature cycles Mean temperature cycle on daily basis and annual year basis of the concrete pavement affect maximum spacing of a contraction and expansion joints in the pavement, and the design values for these factors are dependent upon the geographical location of the pavement. And one more parameter to be considered in the design of rigid pavement, it is foundation strength. Foundation strength is expressed in terms of modulus of subgrade reaction K, which is defined as pressure per unit deflection of foundation as determined by plate bearing test. So, as a limiting design deflection for a concrete pavement is taken as 1.25 mm, K value is determined from the pressure sustained at this deflection. As K value is influenced by test plate diameter, standard test is run with a 75 centimeter diameter plate, beyond which the effect of diameter has been found to be negligible. A frequency of one test per kilometer per lane is recommended for the assessment of K value unless foundation changes with respect to subgrade soil type of a subbase or nature of foundation. Approximate K values corresponding to the CBR values for homogeneous soil subgrades are like this. So it is 2.08 for CBR value 2%, it is 22.16 for CBR value 100%, and it ranges from 2 to 100 for 3% 2.77, 4% 3.46, 5% 4.16, 7% 4.84, 10 it is 5.54, 20 6.92, 50 13.85. The value of K is less than 5.5 kg per centimeter cube when it is tested on the subgrades. Such kind of soil should not be permitted. In case of a rocky subgrade with a K value of 5.5 kg per centimeter cube and higher, the pavement may be laid directly thereon or after providing a level course if it is required. And foundation surface characteristics to be considered. These are smoothness or roughness. These determine extent of resistance to slab movement during expansion and contraction, the account of foundation restraint. And it will affect the joint spacings. Maximum safe spacing increase in the surface roughness of the foundation in case of expansion joint, and it will decrease in case of contraction joint. So this maximum safe spacing will increase with respect to surface roughness, and it will decrease with respect to contraction joint. For the purpose of determination of joint spacings, different type of foundations generally adopted may be classified into three categories according to their surface characteristics: very smooth, smooth, and rough surface characteristics. So if it is very smooth means it is a type of a foundation where compacted sand and gravel, smooth foundation covered with a waterproof paper. So such foundations are classified as very smooth surface characteristics foundations. And if it is compacted sand, gravel and clinker, stabilized soil, rough foundation covered with waterproof paper, that possesses smooth surface characteristics. And then if it is waterborne macadam, soil gravel mix, rolled lean concrete, lime pozzolana concrete, etc., will possess rough surface characteristics. And one thing need to be checked before using in road construction, that is concrete characteristic pavement, its design strength. For economical design, design value adopted for structural strength of pavement concrete should not be less than 40 kg per centimeter square. The mix has to be designed as to ensure that minimum structural strength requirement in the field with the desired confidence level is achieved. We can use the equation S is equal to S bar plus T into sigma. where S bar is the structural design value of concrete, T is the tolerance factor, and sigma is the expected standard deviation of field test sample, where S is the design strength of concrete, which is expected. To achieve a desired minimum structural strength S bar in the field, mixed design in the laboratory has to be made for somewhat higher strength, that is nothing but S, making due allowance for type and extent of quality control feasible in the field. For general guidance, the value of T and sigma of concrete compressive strength of value 280 kg per centimeter square for different degree of quality control are given as, if T is degree of quality control is very good, means a tolerance level of 1 in 15 can be followed. If it is good, 1 in 15. If it is fair, 1 in 10 tolerance level can be followed. And tolerance factor, it is 1.5, 1.5 for very good and good. If it is fair, it is 1.2. And the coefficient of variation, it is 7%, 10%, and 50% for very good, good, and fair degree of quality control. And mixed design can be expected 315, 330, 350 kg per square centimeter for very good, good, and fair. And a standard deviation can be taken as 22, 33, 52 for very good, good, and fair degree of quality control respectively. Modulus of elasticity and the Poisson's ratio for concrete, these vary with the concrete materials and strength. Elastic modulus increase with increase in strength and Poisson's ratio, and decreases with increase in modulus of elasticity. For design purpose, for concrete in 38 to 42 kg per centimeter square, flexural strength range, the following values are used. The modulus of elasticity of concrete is equal to 3 into 10 raised to 5 kg per centimeter square, and the value of mu can be taken as 0.15 for the range of 38 to 42 kg per centimeter square flexural strength. And the coefficient of thermal expansion of concrete of the same mixed proportion varies with the type of aggregates which are used. So the coefficient of thermal expansion is high for siliceous aggregates, it is medium for igneous rocks, and it is low for calcareous ones. However, for design purpose, the value can be taken as 10 into 10 raised to minus 5 degree Celsius may be adopted in all cases. Now you come for design of slab thickness. So in this, critical stress condition need to be checked. So that is that interior loading, edge loading, and corner loading conditions need to be checked. Concrete pavements in service are subjected to stresses due to variety of factors acting simultaneously. The severest combination of which inducing highest stress in the pavement will give critical stress condition. Factors commonly considered for design of pavement thickness are traffic loads and temperature variations. As the two are additives, effects of moisture changes and shrinkage being generally opposed to the those of temperature, and it is of smaller magnitude. So would ordinarily relieve the temperature effects to some extent and are not normally considered critical to the thickness design. So shrinkage and moisture can be neglected. For purpose of analysis, following three different regions are recognized in a pavement slab which react differently from one another. So one is interior loading, second is edge loading, and third one is corner loading. So when load is applied in interior of a slab surface at any place remote from the all edges. And edge loading, it is when load is applied on an edge of the slab at any place remote from the corner. And corner loading, when center of load application is located on bisector of corner angle formed by two intersecting edges of the slab, and loaded area is at corner touching two corner edges. Temperature stresses. These are developed in cement concrete pavement due to variation in slab temperature. Variation in temperature across the depth of slab is caused by daily variations, whereas overall increase or decrease in slab temperature is caused by seasonal variations in temperature. The temperature tends to produce the following two types of stresses in concrete pavement. One is wrapping stresses and another is frictional stresses. Wrapping stresses, whenever top and bottom surface of concrete pavement simultaneously possesses different temperatures, the slab tends to wrap downward or upward induces wrapping stresses. Whereas frictional stresses, as slab is in contact with soil subgrade or the subbase, the slab movements due to uniform temperature rise or fall are restrained due to friction between bottom layer of the pavement and the soil layer. This frictional resistance induces frictional stresses in the bottom fiber of the cement concrete pavement, which varies with slab length. So it can be calculated by using formula SF equal to WLF divided by 2000, where SF is the unit stress developed in the concrete pavement, W is the unit weight of concrete, L is the length of slab, F is coefficient of subgrade reaction, and B is the slab width in terms of meters. And combination of stresses, the maximum combined tensile stresses in the three regions of the slab will thus be caused when effect of a temperature differentials are such as to be additive to the load effects. This would occur during a day in case of interior and edge regions. At the time of maximum temperature differentials in the slab, in the corner region, the temperature stresses are negligible, but load stress is maximum at night when slab corners have a tendency to lift up due to wrapping and lose partly foundation support. Considering total combined stresses for the three regions, that is corner, edge and interior, for which load stress decreases in that order, while temperature stress increases, the critical stress condition is reached in the edge region, where neither of the load and temperature stresses are minimum. And calculation of these stresses, in case of edge stresses due to load, it can be calculated by using formula 0.539 P divided by h square into 1 plus 0.54 mu into 4 log of L by B to the base 10 into log B to the base 10 minus 0.4048. So this is the Westergaard's analysis formula, which is modified by Teller and Sutherland. Whereas P is the design wheel load, H is the pavement slab thickness, mu is the Poisson's ratio, E is modulus of elasticity of concrete, K is the subgrade reaction, L is radius of relative stiffness, P is the radius of equivalent distribution of pressure. So these are all the expressions we use. When it comes to another case, edge stresses due to temperature, this can be calculated as sigma suffix T e equal to E alpha delta T by 2 into C, where delta T is maximum temperature differential during day between top and bottom of the slab. Alpha is the coefficient of thermal expansion of concrete, T is the Bradbury's coefficient, L is the slab length, W is the slab width, and L is the radius of relative stiffness, where Bradbury coefficient depends on capital L by L and W by L. So this is also assisted by Westergaard analysis using Bradbury's. These are all the Bradbury's coefficients. So T is for a ratio of 1, W by L 1. So the Bradbury's coefficient is 0, and if T is more than 12, it is 1. So 0 to 1, the Bradbury's coefficient ranges in between. It goes with 0.04, 0.175, 0.440, 0.72, 0.92, 1.030, 1.075, 1.080, 1.075, 1.050, wet 2, 3, 4 successively up to 11. And then corner stresses. Load stress in the corner region may be obtained as per Westergaard analysis as modified by Elaine. So equation is given by sigma Tc equal to 3p divided by h square